Now I knew there were a number of questions about this homework that's coming to homework 3 that's due. And let's see, had an email about it. Maybe this will help some other people who haven't organized their thoughts about it yet. So I'll just make the questions and respond to the questions in public. Okay. First is 2.7.6 on homework 3. Let's just put it that way. Questions on homework 3. 2.76 and 2.7.8 ask about some counterexamples. They ask you to show that the range of a bounded linear operator need not be closed. The range need not be closed. And the hint, use the linear operator defined in problem 5. And in that problem, you're supposed to show that in fact the operator is linear and bounded. Well, it's kind of obvious that it is. You may assume that it is linear and bounded. They tell you that the norm is 1 in problem 2.7.5. So the question is, do we have to actually do problem 2.7.5? And the answer is no. In fact, I could do it here if you want, just to make sure everybody's happy. Okay? So, hint, use T of 2.7.5. No, you do not need to verify 2.7.5 per se. But maybe it's a good idea to go through it. Okay? In order to use 2.7. So you may use 2.7.5 freely. The answer to 2.7.5 is that indeed a certain linear operator is linear and bounded, and then you're supposed to use that as a counterexample in problem 6 and problem 8. The counterexample in problem 8 is that the inverse of a bounded linear operator need not be bounded. Okay, so what is the operation what is this nice counterexample they're giving for each of these problems? The counterexample is T for 2.7.6 and 2.7.8. 2.7.5 T, L infinity to L infinity, defined by, you take an element of L infinity, which is an infinite sequence that is bounded, and you map it to another infinite sequence. This will be the notation for how an element goes to an element. This arrow with the little bar on the left side. Okay. To C1 divided by 1, C2 divided by 2, C3 divided by 3, etc. Okay, so that's the mapping. That it's linear, you have to add, like C and eta. If I do C1 plus eta 1, C2 plus eta 2, ... that's the x plus y. Okay. This goes to, by definition, C1 plus eta 1 divided by 1, comma, C2 plus eta 2 divided by 2, comma, etc., which is obviously equal to Tx plus Ty. Just write out the vectors as sum of vectors. by the definition of a sum of vectors in L infinity. Okay? So that's kind of obvious that it's linear. Is it bounded? And what's the norm? T of x, okay, what's the norm of Tx? What's the norm of this thing? Well, it's clearly equal to the max, by definition, of the Cj divided by j. J equals 1, 2, 3. Well, soup, I guess, is what you have to do. It's not a max, since the index set is infinite in this case. So, let's see. That's obviously less than or equal to the soup of the Cj's. J equals 1, 2, 3. And so that's of course equal to the norm of x in L infinity. Okay. So that means that the norm of t is at most 1 immediately. All right, you get a less than or equal to 1 times this, right? So that's a bound for the norm. It's remember, Tx less than or equal to Cx is definition of a bounded operator. Bounded operator. And where C independent of x. Obviously. So I think some people had a little bit of trouble with that this week in making that C was not independent of the other vectors. Here you need to, it's independent of all the vectors x. Okay? And then the minimum C that works is the norm. So here we have that the norm of t is less than or equal to 1. Okay? The norm of t is the least C that works. That actually does it. There is such a least C because, in fact, the C is the soup Tx divided by x, which is for a least upper bound. A least upper bound. So there is such a least C. All right? If we go with the real numbers. Okay. And t is less or equal to 1 then by this norm inequality. Now, t equal to 1? You don't really need that.
Yeah.
You don't need that in your problem. But how would you show that the norm of t is equal to 1?
Sequence of all ones, even just the first element 1.
Okay, yeah. That'll do it. Yeah. If I just take the sequence with 1, so to show the norm t equals 1, in fact, one needs only a counterexample. One needs only show a vector x with Tx norm equal to the norm of x. And indeed, you could take x equal to all ones, and then the norm of x is equal to 1. The norm of Tx is the norm of 1, 1/2, 1/3, and so on, which is also equal to 1. All right. And so then you have norm of x. All right. So good. You have done the problem number 5. Okay. It didn't even ask for the norm equal to 1, but it was kind of not too difficult to show it. All right. So that was the first question. The second question on the homework was on problem 2.86. That's a little bit more interesting. They give you two spaces. One is CAB, continuous functions on the closed interval, which you may take to be the unit interval if you so desire. You don't have to work with A and B in general if you don't want to in this problem. I don't care. Or C01. Just make A equal to 0 and B equal to 1. for convenience. Okay? So work with C01 and I'll be happy. And then you have, what you have is that the norm of x in C01 is, I'll just do it in C01 here, is equal to the maximum of x of t in 01. Okay. Now we're going to define another space, C prime 01, which is continuously differentiable functions which is smaller space than CAB, but we're not going to put the same norm. And the norm now on x is going to be the maximum of x of t in 01, an absolute value, plus the maximum of the derivative, t in 01. That will also be a norm. And part of the problem is to show that it is a norm. To go through that, that's not very difficult. Now what you're going to do is you're going to consider now, finally, they didn't introduce this notation in the problem, but I will here, define x equals subspace of C01, not of C prime 01. Subspace of C01 consisting of continuously differentiable functions you were supposed to do something else besides to show that that was a norm in the first part because there was some operator, and I'm going to introduce that differentiable functions and then define Tx equals x prime at 1/2 for x belonging to x. X is itself now a normed space. The norm, though, is this norm. It's just the max norm. Okay? The norm on x is norm x equals the maximum x of t in 01. Okay, so the problem is to show that this operator is unbounded, I believe. Isn't that it? Okay, show that, I'm sorry, this is a linear functional. No. Functional, fx. Linear functional. Okay? Because it's real valued in this case. We'll just take the real valued case if you like. So that's is not bounded. So two things. So it's really define F1. I could really call it this F or F. You got two linear functionals. You could call it a different name. Because using the same name is not a good idea because you have two different domains, right? So one, well, is the same name but a different norm. So I could give it a different name. Let's call this one G. Okay? So that G is mapping X to the real line. You also have define F of X, F from C prime AB to the real line by F of X equals X prime of 1/2. Okay? So what you have is you have the same formula for the functional, and actually the same set of functions it's being applied to. But in one case, you have two different norm spaces. X is one norm space, and C prime AB is a different norm space. Okay. So there's the G. He called it the same letter F, but I'd like to call it a different letter, a different functional G, because it's on a different norm space. All right. So that's what I'll do. So this is the original definition, F from C prime AB. Okay. So I've got two different linear functionals because I have two different spaces. But of course they're given by the same formula on the same set of functions. One is bounded and one is not bounded. So F is bounded and G is not bounded. It's easy to see that F is bounded with norm 1, I believe, and G is unbounded. So how do you show that G is unbounded? Show F is bounded, and I think the norm is 1, while G is unbounded. Okay? So that's a summary of the problem. And you may use that notation in your homework if you like. Okay? Let's see. What did I say? 6. Norm of F is less than or equal to 1. You may actually be able to find the norm of F in this problem. Okay? I didn't do so in my solution. But, okay? Questions about that? Now, how do you show that a linear function is unbounded, or an operator is unbounded? How do you show something is unbounded?
So would you just pick a C greater than 0? The C is probably a bad letter in this case.
Again?
Your definition of boundedness says that the norm of P of X is less or equal to C times the norm
Right.
of X.
Right.
So for that C, we should just say pick C greater than 0 and then find some X.
Okay. Yeah, for every C there is some X so that you get TX bigger than CX.
Right.
So, in particular for every N, because we're working with... so for every N, to show unbounded, G is unbounded. Let N in the natural numbers find X sub N, alright, with G xn in absolute value greater than or equal to N times the norm of xn. Where this is equal to N times the max, therefore, xn of t in 0, 1. Okay. So G of xn is just a real number. Okay. So you have to find a continuously differentiable function. So find xn in this x. So it's got to be continuously differentiable. So something that has a, maybe it's got a maybe you can make this 1, this n, and this 1 over n, okay? Or something like that. Or you can make this n, and 1. It's just by scaling, okay? So that doesn't matter, because you do have a scaling property, right? This can either be small or it could be big. For the same example, just multiply it up, okay? So, all right. So you need the derivative way bigger than, because this is x prime of 1/2. You need the derivative way bigger than the maximum. Okay? That's all. and that's easy to find. Okay, so you should be able to do this with some easy functions. Okay. Last question was, what am I looking for on problem 2.9.6? This was some kind of null space computation, I believe. You're going to have to pull out your linear algebra. It said, give me the, if I have an equation of a plane in 3 space, like x plus 2y plus 3z equal to 0, find a basis for that plane to the origin. Everybody know how to do that? Remember that? This null space computation. Okay. Okay. I think you had to do intersecting planes and lots of other weird things. Okay, null space of a linear operator. So do a null space computation just to actually find a basis. And I think the basis, when you do a null space computation, the fact that the basis is linear, that it really is a basis, in other words, the vectors you find are linearly independent, is kind of standard, that they automatically come out that way by the computation. It's a row reduction method. Okay, so 296, standard null space computation. From linear algebra. Okay, so here's a review exercise. Showing these linear functionals on finite dimensional space are not very difficult. They're nothing more than your linear algebra problem. Okay. Okay, let's go on. Now let's talk a little bit about linear functions and bounded linear functionals and the space of bounded linear functionals, which is what we're coming to today, and then the dual space. We're going to talk about algebraic dual and also just plain old dual. Okay, there's two different things, because one's a vector space and one's a normed vector space. It's just the vector space stuff we'll get out of the way first. That's fairly routine, though it does require a little bit of messing around. Okay, make sure all the definitions make sense. Any questions before we go on? I guess I did have one example more about an unbounded linear functional. So, in the notes, maybe I should do one of these unbounded linear functionals just to make sure we're all happy about it. Let's do one more from notes 3. It had, I took x01. So I used this notation example. One more example here. Example x01 equals space of continuous functions on the unit interval with the norm x equal to the square root integral 0 to 1 x of t squared dt. That is a norm on that space. Okay. And then define f, the linear functional f, from x01 to r. I'll just take the real value of continuous functions by f of x is equal to x at 0. That's a linear functional. So check it. If I take two continuous functions, x and y, of course, then we're talking about x plus y at 0 equals x of 0 plus y of 0 equals f of x plus f of y. Okay, so the linearity just follows by the definition of addition of functions. Okay? So I'm taking continuous function on the unit interval And I'm saying, okay, my functional is just the height at the left-hand endpoint. If I add two functions, then I add the two heights. Okay. Is that bounded? I claim that it's not bounded. So similar type of idea is what you're going to have to do over there. Claim f is not bounded. So what am I going to do? I'm going to see what's the norm. The norm is the square root of the area of the square of the function. So you take the square of the function, you take the area under the curve, then you take the square root of that. Well, so what I need is, let's say I make this left-hand endpoint go to infinity, but I keep the area a constant. Can I do that? Can I make this point go up the axis but keep the area of something constant? The area of the square, I have to be a little bit careful. The area of the square. So when I take this point and I square the function, then it's going to go way up the axis. Okay. But now I want the area under the curve when I do that to be about 1 in size. How would I construct such a thing?
Can we just use... You're saying try and find a function?
Yeah, find a function that the norm is about, on the order of 1. It might be a fraction like a half or a fifth or something. I don't care if it's...
that one. What about just x to the 1/2? That work?
X to the 1/2.
Because then you integrate that, don't you get 2/3 x to the 3/2? 0 to 1, so it's just 2/3. But then if you square it, you get 1 over x. And that's like...
Oh, I see what you're saying. You want x to the minus 1/2.
Oh, yeah, sorry.
X to the minus 1/2, the only problem is that's not a continuous function.
Oh, yeah, because it's a closed... Oh, I didn't... Yeah, I misread it.
Yeah, that's a good idea. It just didn't work. But let's say I'm going to take again a sequence of functions, xn. I need to to show something is unbounded, I need to take a sequence, basically. I need to show that the norm is not less than or equal to n for every n. So I'll need a sequence of functions, xn, to do this job. You can't do it with just one function. Okay? So what I'm going to do is take something that looks like, just take it as simple function as I can, linear, and then 0 here, and see if I can fix it up. Okay? Now I need the area to be about 1 after I square it. Okay. Well, if I square this linear thing, I'll get some kind of, quadratic thing, but big deal. So, okay, so then if it's quadratic, it's still going to kind of look like a triangle. Base times height is area. I need the height to be big. And so that when the height is squared, the area is about 1. So I'll take square root of n and 1 over n. Okay? And that does the job. Okay? This is my xn of t. Okay. And so this xn of 0 is the square root of n. That's okay. And now what's the norm of xn? The norm of xn is the square root of the integral 0 to 1 of xn of t squared dt. Now I just have to calculate this norm. Well, I'm going to do the integral by an easier function. I'm going to basically take this function. If I square this function, I get the same answer if I square that by symmetry. Okay? This is an easier function. All right, this is 1 over n. This has got to be the square root of n. And this is still a straight line. Okay? So I just have to do this integral, the square of this one. This is xn's little brother, but it's just that it doesn't evaluate a square root of n at the left-hand endpoint. But the norm is the same. Okay? So So this is what y equals the square root of, let's see now, it would be n squared of nt or something like that. Y of t equals this. Okay, for 0 less than or equal to t less than or equal to 1 over n. So the norm of this thing, the norm of y, and then y equal to 0, where 1 over n less than t less than or equal to 1. So if I define this function, then the norm of y equals the norm of xn. And what is this norm of y? This norm of y is the square root integral 0 to 1 over n of n squared of n t, the quantity squared, dt, equals, let's see, I'll get an n cubed integral 0 to 1 over n t squared dt. The antiderivative of t squared is t cubed over 3, so you can see the n's are going to cancel. So you're going to get n cubed over n cubed times a third equals the square root of a third, which is what I wanted to show. It's a number that is constant, whereas xn of 0 is the square root of n. So xn, so what's it? What's the functional? F of xn divided by the norm of xn equals the square root of 3n goes to infinity. All right. I can put absolute value signs here if I like. It doesn't make any difference in this problem. Therefore, the norm of f equals infinity. Okay, doesn't exist. All right, as a finite number. Okay, it's unbounded. All right. Now, let's go on to the rest of this material that you're supposed to have finished for your homework, though you didn't have to really use for anything in your homework this week. You had to do a little bit of calculation with the dual basis. The dual basis, which is a fairly simple idea. But let's talk about the dual. What's the algebraic dual? Let's go ahead and let's take a vector space. So today, well, for much of the time, I'm only going to be working with vector spaces. I'm only going to get the norm vector space at the very end. It looks like, okay, because it's spending a lot of time on this. So x star, so x equals a vector space. X star is the dual. Algebraic dual is called. There's two. Corresponding to the fact there's only an algebraic structure on a vector space. And what is that? This is just simply the set, the vector space, it actually turns out, the vector space of all linear functionals on X. Okay? Now, is that a vector space? It's almost trivial to check, but let's check it. So F what is it? We already have linear function is a function at the root of it, right? So by function addition, definition of function addition, f plus g at x equals f of x plus g of x. That's basic. Okay? and also CF at x means, well, alpha x. Alpha f at x means alpha times f of x. Okay, that's the definition of functions. Okay, there's no functionals in there yet. Okay, now let's check that x star is a vector space. That should be an elementary exercise, but I'll do it anyway. You have to show that f plus g is having this is linear. You have to check that f plus g at cx. Oh, excuse me, alpha x. F plus g at alpha x equal to alpha f plus g of x. Okay, and you have to check. Must check 1 that f plus g is a scaling. Okay, and 2 f plus g at x plus y is equal to f plus g at x plus f plus g at y. That will show that the sum is in the space of a linear function, because a linear function has to satisfy the property that it has you can pull the scalars out and that you can add. That is, the functional of a sum is the sum of the functional values. So you have to check these officially, right? To check that it's a vector space. Is everybody kind of following that? I want to check that f plus g is again back in. Let f and g belong to x star. I must check that f plus g is again in x star. And so I need to, this will give these two, 1 and 2, imply that f plus g is in x star. I also have to check that if I have f in x star, then alpha f is again in x star. That's even easier. So let me just check this one. So 1 is fairly immediate, I guess, isn't it? Think you can do all these? Yes. Okay. Let's see. Yeah. F plus g at alpha x. Okay. Well, first you have to use the function definition. Okay? So that's f at alpha x plus g at alpha x. Then use that f and g are both linear functions. So you pull the alphas out. Okay, and then you get to this. Alright, so these are elementary. Alright, so I just wanted to write down what you have to check that it is indeed a vector space. Now let's consider a dual basis. What's a dual basis? Let x be a finite dimensional vector space. We're going to worry about the finite dimensional case first. And with dimension n. Okay? And let E1 through En be a basis for x. Then there's something called the dual basis corresponding to this basis. What is that? Well, so I want to talk about dual basis. First, if f is in x star, so we have any linear functional on x, And if I represent little x in capital X, my original vector space, in terms of coordinates in this basis as x equals summation Cj Ej. J goes from 1 to n. So again, we're going to use C1 through Cn is going to be the standard coordinate representation of x. Then I can always write f of x by the fact that it is a linear functional as summation Cj f of Ej. That's just a general formula because I mean in later problems you're going to want to know that this sum is convergent. Okay, let's say in an infinite dimensional vector space, and that will be only the case if you have a Schauder basis. Not all the spaces we studied so far have such a Schauder basis. Anyway, you want to know if this converges in the norm. If you have an infinite sum. We're getting there in a little bit. Okay. So, but here there's no norm even. Okay? Because it's only a finite sum, so there's no even need for convergence. Okay? See with it? So all of these topics are relatively elementary in the finite dimensional case. So everything's algebraic. So you just have this. And we'll just say, well, the f Ej has to be something. F is a fixed thing. F of Ej. Ej's are my basis elements. This has to be summation Cj gamma j for some scalars. I'm going to call them gamma j because of what we're going to do here for this next week's homework. He calls them alpha j, but when he gets to section 2.10, he's going to be calling them gamma j's anyway. So I'm going to call them gammas here. So those are scalars. So f is equal to f sub gamma 1 through gamma n. In other words, the gamma 1 through gamma n determine f. And so it's just a linear function of the standard coordinate. That's standard coordinates. Okay, this is a linear function of those standard coordinates. Okay, real valued linear function. That's just what a linear functional looks like. All right. So now, if I'm going to specify certain linear functionals, which I'm going to special ones. So define f1 equals f sub 1, 0, 0. So take the standard basis vectors in Rn and use them as the gammas. All right. Define f1 equals this, f2 equals f sub 0, 1, 0, ... 0. So the e1 through en might not be the standard basis vectors, they're just some general thing. All right? In fact, there might be some other basis, right, if you're working with Rn. But now we're going to take the dual basis relative to this basis, e1 through en, is going to be defined like this. So in particular, f1 of Ej is the gamma j. What is that going to be? According to this, it's 1 if j is equal to 1, and it's 0 otherwise. We call that delta 1j. That's the Kronecker delta. Equals 1 if j equals to 1, and 0 if j is unequal to 1. Anyone never seen this Kronecker delta? Oh, maybe you haven't. But anyway, it's around, so we're going to use it a little bit. Some people are really good with Kronecker deltas, and you'll see it. And then f2 of Ej is equal to delta 2j, all right, etc. And fk of Ej is delta kj. So that's how you could write it. J and K equals 1 to n. So using J as the index for the original basis, K is the index for what we're going to call the dual basis, because the claim is that indeed F1 through Fn, which is going to give you n different linear functionals, which would be what? f1 of x is c1, f2 of x is c2, right? So f1 of x is c1, f2 of x equals c2, and so on. fn of x is cn, according to the standard coordinates. All right, those are the n linear functionals. Claim these n linear functionals form a basis. Forms a basis of x star, of the dual, algebraic dual. Okay, and that's, so then in that case, then we'll have the dimension of x star is equal to the dimension of x. Let's see that. Let's see, that's easy to prove, I think. First, linear independence. Assume summation beta k fk is identically 0 on x. All right, so that's the zero linear functional. K equals 1 to n. All right. So in particular, so that means, so that what does that mean? So that, i.e., summation beta k fk of x is equal to 0 for every x in my vector space. I want to show that all the betas must also be 0. I should have made you do all these problems in your homework. Alright, this is just the standard material. So you show all of this. Now how do you do that? Well, okay. You can go pick your x's to be special cases, like the original basis vectors, and that's how you do it. So take x equals ej for any j. And then you get that, by plugging that in, you get the Kronecker delta fk at ej equals delta kj. Obtain summation beta k delta kj equals 0. This is the sum on k goes from 1 to n. When you do this delta operation, you get j is fixed, so you're just getting this sum is beta j. So beta j equals 0. But that was true for any j, so all the betas are equal to 0. Beta j equal to 0. Okay, so that shows linear independence. So this is check. Okay? I guess I should put an arrow up to that so it's clear. Okay? Okay. Now, you need to show that it spans. The basis spans. Well, obviously. Because anything, Cj gamma j, can be obtained as summation gamma j f1 through fn, obviously. I just put the gamma j in front of fj and I add, and I'm done. Also, f of x equals summation ck gamma k. Here I'll put the k's in instead of n, is equal to summation fk of x times gamma k. K goes from 1 to n. So someplace I changed my index from j to k. Alright? This means where again x was equal to summation cj ej. So I'm going to write everything in terms of this coordinate vector c1 through cn.
I'm a little confused. You're saying that there, but then over there you say take x equals e sub j just for a single j?
Yeah. Here I said, assume I want to show linear independence of these n functionals. I have n functionals.
So you're doing them one at a time then, you're saying?
I have n functionals, and I want to take a linear combination and assume that's the zero functional. The zero functional. Okay, because that's what we said. The X star was a vector space. What is the zero element of that vector space? The zero functional. In other words, every vector gets sent to the zero number.
Right.
Okay. So the zero functional is that's what I mean by the triple equal here. Okay. So this linear combination of functionals is again a functional. Okay. I assume it's the zero functional. That means that beta k f k x is equal to 0 for every x.
Right.
Okay. So in particular, if I take x equals to ej, x was the element in our original vector space. In particular, if I take x equals ej, then I get 0.
Right.
So if I plug that in and just see what happens, I get beta j equal to 0.
Right. So you're letting in there. You're just saying for any fixed j.
Yeah, for any fixed j, beta j is equal to 0. But since j was arbitrary,
it shows it for all the j's.
That's right.
Okay, I follow that.
Equals 1, 2, up to n. Okay.
Okay.
Now you follow it. Okay. So that showed linear independence. Now I want to show that indeed these n functionals span the whole space. I need to do an example so we can see this in hard life. Okay, what everything is. It's a bit of a mess until you do so. So I'm just saying I have these n functionals, and clearly then I just want to get any linear combination looking like this that's all possible linear functionals, because any f had this form. Okay? So I just take the gamma 1 times f1 plus gamma 2 f2 and so on. So that's this. Okay, so it does span. So f1 through fn span x star. QED. So the theorem is done, I think it's 2.9-1, that x star has dimension also n, when the dimension is finite. Okay. So in fact, if dimension of x equals n is less than infinity, then dimension of x star also equals n. Okay, I think it's 291. That's where we are. Okay, but I'm going to skip a little bit. Yikes! Get through all this junk. Let's see. Maybe we should do this little example on the bottom of the last notes 3. Still, it's the very last example that I did. It was a little bit harder than the ones you did, in fact, in the book. It looked like, but not many harder, really. So I'm going to define let x equals R3. And let y equals eta 1, eta 2, eta 3. I'm going to define my linear functional in terms of standard coordinates, okay, in terms of coordinates relative to the standard basis, okay? And so I'm calling it y, and define f of y equals eta 1 plus eta 2 plus eta 3, okay? All you're ever getting is a linear combination of coordinates, okay? But the coordinates have to be from some relative to some basis. And here I took the coordinates relative to the standard Euclidean basis, 1, 0, 0, 0, 1, 0, and so on. Okay? And to define some linear functional. Okay? And now I'm going to take a different basis. Okay? And I want this dual basis relative to that for this particular. Well, then first I want the dual basis, then I want to find the representation of this f in terms of the dual basis. So let now E1 equals 1, 1, 1. E2 equals, I just took kind of a basis that I could come up with, and E3 equals minus 5, 4, 1 be a basis of R3. Okay. Find a representation will be a unique representation. Find the representation of f in terms of the dual basis f1, f2, f3 relative to this given basis e1, e2, e3. So according to that, this is the unique representation. Right here. It's gamma k fk of x. Okay. Or fk of y. So what do I have to do? I'm erasing all the good stuff. To remember it. Okay. So what do I have to do to find representation? I'm not even going to compute the dual basis first. What is the representation? What is the what are the gammas? Well, gamma 1, okay, is just f of E1, okay. Gamma 2 is f of E2, and gamma 3 is f of E3, and then I write f equals gamma 1 f1 plus gamma 2 f2 plus gamma 3 f3. Okay? So that's my prescription. Okay? So it's simply going to have gamma 1. So gamma 1, the coordinates of f relative to the basis. In other words, I have the coordinates. I want to find the coordinates of f relative to this dual basis. And any time you're doing vector space things, you want to find the coordinates of something relative to some basis. So I just want the coordinates of f relative to this dual basis. And here's the prescription. I don't even have to do any work. I just plug in. So gamma 1 is equal to that f of E1. What's f of 1, 1, 1? Well, it's just 3. Okay. Gamma 2 equals f. So I gave the easy problem. F of 1, 2 minus 3 equals 0. And gamma 3 is equal to f of minus 5, 4, 1 equals 0 again. Because I'm adding the coordinates according to the definition of what f is. Adding the coordinates relative to the standard basis of R3. Okay? So that means that f is equal to 3f1. Okay? So the thing is, what you have is you have two different representations of f. One with respect to the standard basis. Okay? And one with respect to then one with respect to this dual basis. Actually, the dual basis of the standard basis would be kind of trivial as well, right? So that would give you something else. So you have a representation relative to this dual basis. 3f1 plus 0f2 plus 0f3. Okay, let's do something a little bit more interesting. How about if I wanted to find the f1 at the 1, 0, 0? What's that? What is f? So this is part A. B. Find f1 at the vector 1, 0, 0. How do I do that?
You just use that expansion you have there. Basically hit both sides of that with 1, 0, 0 on the right, and then divide by 3. And then use the expression over there on the left, the original f.
I guess that's going to work because of how easy this was. If I was going to find f2 of 1, 0, 0, that's a little bit harder.
Yeah, so you don't have to do...
Okay. Let's see about that. So you're saying, yeah.
It seems trivial in this case, but it's fun.
Yeah, it is by this one. So that's a good point. So I can just apply both sides of this to 1, 0, 0, and I get f of 1, 0, 0 equals 3 f1 of 1, 0, 0. So I get f1 of 1, 0, 0 equals 1/3 f of 1, 0, 0, which is 1. So this 1/3 times 1 equals 1/3. And I did it another way, which would be the...
It's a better way, probably more general.
No, there was a general way.
Yeah,
there's a more general way. The more general way is to solve equations. But since this was so lucky, okay, that I got these two zeros here, all right, then you were able to get the shortcut. Very good. Very good. So this is the answer. More generally, then you would solve for the coordinates of 1, 0, 0 relative to the basis. Okay? You'd solve x equals 1, 0, 0 is equal to c1 times 1, 1, 1 plus c2 times 1, 2 minus 3 plus c3 times minus 5, 4, 1. I believe that's what I had there, isn't it? Yeah. So you would find the coordinates of x. You would find c1, and then you would say f1 of x is just c1. f1 of x is c1. Alright? So I need to find c1. Well, it turns out that solving for c1, if I call this star, solving for coordinates of x equals 1, 0, 0 in star, we obtain, that's not very difficult either, if you realize that these are mutually orthogonal, the 1, 1, 1, so you can actually, that's what's going on here. Okay. So, we obtain C1 equals 1/3, C2 equals 1/14, and C3 equals to minus 5 over 42. So that means that I've actually could calculate F1 of F2 of 1, 0, 0. F2 of 1, 0, 0. Therefore, F2 of 1, 0, 0 is equal to 1/14, and F3 of 1, 0, 0 is equal to minus 5 over 42. I need one more theorem before we go today. Okay. Comments about this? These are elementary linear algebra calculations. We're just going through the definitions. Okay. Okay. There's something called the second dual, which I'm going to have to cover. And talk a little bit about isomorphism. So what's the second dual? Second algebraic dual. This is simply going to be the dual of x star, which is called x double star. Surprise, it's not a very difficult notation. What is that? Well, okay, claim. Any x in my original vector space is an element gives rise to an element. G sub x in the second dual. So what am I talking about? G sub x is mapping the dual space back to this field of scalars. Okay. So I could talk about the real values or whatever here. So K was my scalar field. How is that going to be? What's G? So I have to take Gx of f. How's the claim? How is that? Any x gives rise to that. How is x going to come into this formula? So I have to take f is going to be something in the dual space of these linear functionals, and I have to apply and g of x is going to be a linear functional on the dual space. Okay. So how could that be? Well, this is the formula that's simply going to be f of x. Okay. In other words, you fix x as a domain value and let f run. Okay? And that gives you an element of the second dual. It's a function of f. So you can see the duality coming in there now. You fix the little x and you let f run over all possible functionals in x star. That's a linear functional. Okay. All the linearity, I'm going to skip all that. Okay. What you have is that so what you have is that you have a mapping from x to the second dual given by x goes to this g sub x. Okay? And so everything in x is included in everything in the x double star. Now, is that a one-to-one mapping? It doesn't necessarily be onto in general, but is it one-to-one, let's say in finite dimensions? Let's check that it is one-to-one in finite dimensions. The author claims that it's injective, that is one-to-one in general. Okay? But we're actually not even going to show it for normed spaces until we get the Hahn-Banach theorem. So the fact that it's injective in general looks a little beyond us right now. He makes the comment in there. So he doesn't make too many comments just so, well, it just so happens that blah, blah. He doesn't give a reference for it. Okay. So you may get, I got a little bit saying, well, let's at least look and see what it does for norm spaces. He kind of just drops it because he's not going to worry about the general injective problem for a vector space. He's only going to work with norm spaces anyway. But, so injective means one-to-one in case you're reading. Is it? Okay, so here's the question. Is it one-to-one? Well, it is linear mapping. I'm going to skip all that business, too. It's kind of obvious from the canonical form. It's called the canonical, C for canonical. All we're doing is just looking at it in a different way. Right? We have f of x, just looking at f as the variable, and x is the fixed thing. Okay? So, that's the canonical version of canonical. Let's see. So the claim is 293. Let's see what the claim is there. I think it's 293. No, it's 292. The theorem is if x is finite dimensional, then C is one-to-one as follows. Let E1 through En be a basis for x, and let x naught equals summation C naught j Ej be a fixed element of x if f of x0 equals 0 for every f in the dual x star, then in fact x0 must equal 0. So that means the null space of C equals the 0. Okay? In other words, what does it mean for the null space of C to be the 0? It means that I set the gx equal to 0 and I find out what all the x's are. Okay? The gx being the 0 mapping simply means that f of x0 is equal to 0 for all f. gx0 equals 0 mapping simply means fx0 equals 0 for every f in x star. Okay. So how do I show that x0 must be 0 then, in that case? Well, it's trivial. f of x0 equals summation c0j gamma j equals 0 for every gamma 1 through gamma n, because it was true for every functional, and the gamma 1 through gamma 1 give you every functional. Okay. So if that's 0, then in particular it's true when gamma 1 is equal to 1 and all the other gammas are equal to 0. Okay? So in other words, that means that C01 has to be 0. Alright? Which implies, in turn, by C01 equals 0. C02 equals 0. And so on up to C0n is equal to 0 by applying all the gammas as the delta jk, basically. Apply. Gamma 1 equals 1, gamma 2 equals 0, equals and so on, equals gamma n equal to 0 to give that C01 equals 0, okay, etc. So, therefore, x0 equals summation 0 ej equals 0, which is what I wanted to show. So, what's the corollary of this? Is 293, and that's it for chapter 2.9. 2.9-3 gives that the dimension if dimension x equals n is finite, then the second dual is equal to x. Okay? So in other words, this mapping is onto. Okay? Or it's isomorphic, I guess is what we say. Isomorphic. Okay. Where isomorphic means that C is an isomorphism means that it's linear, and it's bijective. Linear and bijective. That's an isomorphism of vector spaces. Okay. All right. Well, I guess I can't say anything else because we're out of time. So, have a look at that. You all knew the linear algebra behind that one, I believe, because you all did it on your homework correctly. But the proof of 2.9-3. So I think I'm safe to skip that. Everybody tried the extra credit problem, I think. And so they understood.
What did you give on the extra?
I only gave 2 points for that.
Every time, or is it changed?
If it was a really hard one, I might give +3.
Yeah, because you just put like a plus.
I put a plus sign. Normally, on an extra credit problem, it's a standard would be a +2. You could get half of it for +1, or all of it for +2. And I don't give, and I might give a 1.5.
I think I got that on the last one.
Okay. So it's plus points. Those are plus points. Thank you very much.